Hello, thanks for joining our EMC Best Practices seminar. And I just want to thank you in advance for the overwhelming support that we've gotten. It motivates us to keep doing these and do more of them. My name is Tim Horacek from Amitech Compliance Test Solutions. You probably know us from our brands EMTest and Tezek for the automotive world. And let's get into it. Today's topic is about dropout testing. Are you doing it wrong? And I want to make one point before we start that things you learn today will also apply to other types of testing, for example, Pulse 4. And while the presentation today is about dropout testing, dips and drops testing, the things that you learn, especially about switches and 4-quadrant sources, can apply to other types of testing as well. So dips and drops testing is usually split into two different categories. A dropout is to 0 volts, and a dip testing is to something other than 0 volts. You'll find cases where the DUT has to react correctly for a short period of time at 0 volts, or it may fail, for example, at 6 volts, but it has to work at 8 volts. So basically, a dip is to something other than 0 volts, and a dropout test is all the way down to 0 volts. We're going to talk about both of those types of testing today. So it's worth taking a couple moments to think about what happens in the car. Basically, in the car, everything is in parallel all the way back to the battery. So every DUT sees the impedance of every other electronic subassembly in the car. There are exceptions. For example, an open circuit event would be a loose or bouncing contact, something like that. So the DUT would see an open circuit back to the rest of the vehicle. And that's one of the things we're going to talk about today. And it kind of makes a difference to how the DUT behaves, how the test equipment should be, and it has a large effect on just everything about the test. On the other hand, very often people say, oh, a dip test is a simulation of a fuse blown into the vehicle. You find that written in some of the standards. So a fuse blown into the vehicle, assuming it's not the fuse that powers the device on our test that we want to test, if it's a fuse somewhere else in the vehicle. So that would be a large load on the rest of the vehicle, and that would result in a voltage drop as seen by the ESE that we are testing at the moment, the DUT. And so as soon as the fuse burns completely through, well, then the voltage returns to normal. So that's one of the reasons for dropout testing. And so basically it comes down to two different kind of classes. It's a high impedance as seen by the DUT, so an open circuit type event, a bouncing contact, or a loose contact, bouncing relay, or a low impedance event as seen by the DUT. Something else in the car is causing intermittent or bad voltage as seen by this electronic subassembly. So here we're going to show what I just talked about, the kind of two different types of testing. And there's some hints in the standard that explain or give you hints about what type of equipment or what type of simulation that the standard writer intends you to do. So here at the top right-hand corner, we see an example of the ARB plus the source, plus a DC source or a programmable source. And you see that it says the rise and fall time shall be not more than 10 milliseconds. Rise and fall time is typically defined in the automotive world from 10 to 90% of the event that we're simulating. So this is relatively slow, not more than 10 milliseconds. On the other hand, you have from a manufacturer standards, you have both TR and TD are less than 1 microsecond. Now, as great as the our battery simulators are, and 4-quadrant battery simulators in general, as great as they are, 1 microsecond is too fast for the state-of-the-art battery simulator. So this already gives you clues that, so the top one is with 10 millisecond rise and fall time, that you can do with a programmable source. The bottom one using a dropout switch, because it requires a rise and fall time of less than 1 microsecond. So those are already 2 clues about what's the standard writer intend for me to do. It's also worth mentioning that we'll come back to this in a minute, but generally DIPS testing, so something other than 0 volts, is done with a programmable source, 4-quadrant source, and generally a dropout test that drops to 0 volts is performed with a switch. It's just not as easy to program or to set up to get your test setup running with a switch that doesn't drop to 0 volts. Is technically quite challenging to do. So let's take a moment to look at what happens to the DUT during the testing, either what happens in the car in a low impedance or a high impedance event, or specifically in this case, I prepared a couple of simulations to show what happens to the DUT, current and voltage curves, during different types of events. So the first simulation I prepared is a high impedance simulation, and this simulates like bouncing relay contact, loose contact in a vehicle, something like that. And as you can see, the voltage curve is the green curve, and it slowly falls off. But the speed at which it falls off depends on the impedance of the DUT, how much power it consumes, if there's some kind of parallel loads to the DUT. But what you can clearly see is the voltage falls off quite gradually. Actually, it's an exponential curve until you power the voltage, until you power it back on. Then the DUT will power back on, do its function. Usually you do some kind of monitoring of the DUT to make sure that it's returned to its standard condition after the event has been removed. So now let's compare that to a low impedance event as seen by the DUT. So first you can see that the battery switches off relatively quickly. That's because it's a 4-quadrant source. We're going to explain a 4-quadrant source in a minute, but it basically means that a source that can sync and source, so it accepts feedback from the DUT and will discharge the DUT. So you have a relatively fast switch off from the DUT, and you also get a relatively heavy peak as the DUT is discharged through the 4-quadrant source. Of course, when you power the DUT back on, you get another current peak as the DUT starts up again. So let's take a moment to kind of compare and contrast the 2 different methods. So a low impedance simulation is much more likely to cause the DUT to reset over a given time frame, and that's because low impedance source would discharge the DUT if there's any kind of buffering in the electronic subassembly. There's a good chance that for a high impedance event, the DUT will withstand that. However, a low impedance event will also discharge any capacitance that's in the test setup or in the DUT, and is more likely to cause the DUT to reset. Also, a low impedance simulation is much more likely to cause overheating due to the DUT. Basically, it gets double the current flow, even more, as you switch off the DUT and the DUT is actively discharged by the low impedance source, as it would be in a vehicle, of course. That active discharge has a heat penalty that can cause some DUTs to reset, to overheat. It can be, with a low impedance simulation, it can be easier to support a dip type test. And the reason for that is because you're using a programmable source for that. Normally we use a 4-quadrant source, and a 4-quadrant source has the benefit that you can influence the rise and fall time, but it's not infinitely fast. The source has a very specific rise and fall time that is slower than you would get with a switch, a high impedance simulation. And finally, it's the best way to do other types of simulations in the vehicle, except for capacitive transients, of course, capacitive discharge transients. You could do pulse 4, you can do pulse 2B, you can do other types of tests with a low impedance 4-quadrant battery source. Now, a high impedance simulation is more likely to allow the DUT to avoid a reset condition, because depending on how long that dropout is, it could be that the voltage doesn't drop enough to cause a reset condition in the DUT. But it depends on the time. Obviously, this is just capacitance in the test setup, capacitance in the DUT, so this is an exponential shape. And that all depends on the time and the current consumption of the DUT and parallel loads. The results do, however, heavily depend on any types of parallel loads. So not every laboratory has any kind of parallel loads. They simulate some other way or not. That should be documented in the test plan. The disadvantage, the real disadvantage of a high impedance simulation is that it requires some very specific loads to do that. Obviously, if you just go open circuit, there's no real way to verify the fall time. Even in some cases, it's so extreme that you can't even see the dropout. There's no way to verify that. It's a more complicated. You usually have predefined loads. Amitech, EMTest, and TESEC, we make those, and but those loads are required for any kind of dropout test, a high impedance dropout test. Finally, you have the benefit of a high impedance simulation in that it's really the only way to simulate loose contacts or bouncing relays, those open circuit events in the vehicle. So now let's talk about 4-quadrant sources. 4-quadrant sources mean that the DUT can accept negative current coming from the DUT. Of course, every power supply can provide positive voltage and create positive current to the DUT, but if you change the voltage down, then you're actually accepting the voltage change results in a negative current going back to the DUT. That's this quadrant 2. So positive voltage, negative current, you don't get that from a power supply. There are also some other use cases. For example, quadrant 3 is negative current, negative voltage. If you had to do like a reverse polarity test, and that's possible only with a 4-quadrant source. And finally, you have negative voltage, positive current. So if you went from, say, -12 up to -8 volts, you would actually have positive current for a moment, but still negative voltage. So one of the main benefits of a 4-quadrant source is it can discharge the DUT. And that's important because that's what happens in the vehicle. So all those parallel loads to the DUT, the extremely low impedance battery in the vehicle, those will discharge the DUT in the vehicle. So as I said, it can sink and source current. The 4-quadrant source is also typically much faster, both in bandwidth and rise and fall time, than like a classic laboratory power supply. And rise and fall time and bandwidth are actually related. There's a kind of a rule of thumb that's called rise time is equal to 0.35 times over the bandwidth, the 3 dB bandwidth of the source. You can also adjust the rise and fall time. So if you want a very specific rise and fall time, you can program that within the limits. It can never be faster than the source can, switch, high or low. But you can effectively adjust the rise and fall time based on the control signal from an arbitrary waveform generator or something like that. Just a hint to standards writers, usually it's better to define an actual rise and fall time instead of slew rate, because slew rates is what happens in some amplifiers, not our amplifiers, but some amplifiers. when they're absolute on their limit of rise and fall time. That's the slew rate. And there's really no way to program that. But if you use an arbitrary waveform generator, you're programming the actual switch off time, for example. If you could program that, you have a little bit more control over how the user is able to influence program the test. Some examples of 4-quadrant sources, there are a lot of them out there, but at the moment we have almost exclusively 4-quadrant sources with our Arvidius 200Q. Came out a few years ago, and the PA5840 available from Tesik. It's important to note that most power supplies can only perform basically quadrant 1 type tests. That's positive current, positive voltage. You don't get any kind of negative current feeding back to most laboratory power supplies. So it's kind of important to understand what a 4-quadrant source is when you're thinking about what happens in the vehicle. The battery in the vehicle is low impedance, therefore my test setup should be low impedance in that case. So now let's talk about dropout switches. Dropout switches typically don't discharge the DUT, although there are several use cases where you want to, and we can. I'll explain that in a moment. They always use some kind of fast semiconductor switches for repeatability. There are some standards that require electromechanical switches, relays. For some testing, when required, we'll do that. But most dropout switches are semiconductor switches, and they have several benefits. The main benefit really of a dropout switch, even though it's not exactly what's happening in the vehicle, you can calibrate it. They have very high repeatability, and you can calibrate them in a ISO 17025 accredited laboratory. They are high impedance when open, not giga ohm range like an electromechanical switch might be, but typically in the something around 1 mega ohm, maybe a little bit less than 1 mega ohm, which is for the purposes of test quite acceptable, especially when you consider there might be parallel loads in the actual vehicle, but they're high impedance when open. They also switch faster. As good as the amplifiers are, there are no amplifiers that can switch in less than one microsecond. The main disadvantage of using a semiconductor switch is that the rise and fall time is kind of based on the design, and there's really no way to influence it where you can with a programmable 4-quadrant power amplifier. So the exception I was talking about, where they normally don't discharge the DUT, there are some new requirements of LV124, for example, where you need to discharge the DUT. There's a secondary switch called S2 in the standards, negated to S1, that will rapidly discharge the DUT. It gives quite similar results to using a 4-quadrant amplifiers. There are other switches with other features, like we have one that also does dropout interruption on signal lines, data lines. We have switches that can switch between 2 different voltages. We even have all of our modern switches also will support interruptions on BAT minus, so battery return lines. So let's talk about what we've learned so far. There's a big difference between a high impedance switch and a low impedance DC source to the DUT. It gives dramatically different results. Really, knowing the difference can help when troubleshooting the DUT. We do have cases, people call up support line and say, hey, my DUT is acting differently when I test it this way than it does when I test it the other way. That I hope you've learned today can help you troubleshoot these kind of unexpected differences between 2 different test setups. However, both methods do have their ways. I mean, both open circuit, as seen by the DUT, and a low impedance events are found in the vehicles. I think there's a case that there's a need for both types of testing because of the things that happen in the vehicle. Finally, I hope you've recognized that power supplies are not 4-quadrant sources. Yeah, even the most power supplies, good power supplies, won't meet the requirements of the standard. Neither for slew rate, bandwidth, stability, reset behavior, things like that. We only recommend, unless the standard specifically demands it, semiconductor switches used for high impedance testing. It is possible to pass with one method and not with the other. Finally, I hope that there might be a couple of standards writers. I am on the standards committees, but my standards mostly EMC. But I hope some standard writers take this and try to make the intent of the standard much more clear when you're writing it. But for the users, if it's not clear, ask. Write it in the test plan if you have to. If nobody can give you a satisfactory answer, put it in the test plan. Explain exactly how you tested it. So that brings us to the end of the discussion about battery simulators, dropout switches, dips and drops testing in general. I hope you've learned a lot. I've been watching the comment section as we've been going, and we have got some good comments already came in. So if you have any last minute questions, type them into the chat section, and let's look at the question and answers. A lot of questions about am I doing it wrong? Actually, no. This, of course, was a little bit of a catchphrase. Am I doing it wrong? There are two accepted methods. Both methods work. They both have their place. There were also questions about, in my specific vehicle application, I make a body control module or whatever. Yeah, it all comes down to really what is the intent of the standard, and so. But you do get different results, and therefore, to reiterate a little bit, my closing comments is you should always document that in the test plan, and of course, whoever's commissioning the test, they have to sign off on that. So it should be clear. If they can't answer, then you write the test plan, and by default, you're doing it right with a good test plan. The other question was about power supplies. Can I use a power supply? Lots of questions about that. What happens if I put a series resistance in my power supply? Will that discharge the DUT? Yes, but you may recall ISO 17637 states that the source has to have a source impedance of less than 10 milliohms, and so unless you have a massive power supply, really massive power supply that can accept a 10 milliohm load and your DUT. Generally speaking, just putting a resistors in there is pre-compliant. Something not quite compliant, maybe something that you want to test before you send it off to the fully compliant laboratory, and that kind of thing. But that pretty much sums up the questions that we have so far. Thanks a lot. We're blown away by the attendance, and have a great day.